In this video, we're going to talk about a new vector. It's called the gradient vector, and we're going to look at it first in 2 dimensions. The directional derivative can be written as the dot product. We saw that in the earlier video. So that my directional derivative of f of ab is given by the dot product of the vector with components fx, fy evaluated at ab, dotted with the vector u sub 1, u sub 2. The vector fx of ab, fy of ab is an extremely important vector on its own, and we call it the gradient vector. It even has its own notation, which we're going to see in a minute. So if we let f be differentiable at the point xy, the gradient of f at the point xy is the vector valued function given by the gradient of f of xy is equal to the vector with components fx at xy, fy at xy, or in vector component form, fx, xy in I hat direction plus fy, xy in the j hat direction. You'll notice the notation here of an upside down triangle. This is the gradient notation. Now, using the definition of the gradient, I can rewrite the directional derivative du of f of ab as the gradient of f evaluated at ab dotted with the vector u. The gradient vector satisfies the sum, product, and quotient rules that are analogous to those that govern ordinary derivatives. Let's work an example. I have a function f of x that's given by 4x squared minus 2xy plus y squared, and I want to compute the gradient at the point P given by the coordinates -1, -5. If I graph this function, I get part of an elliptical paraboloid that opens upward and has one vertex at the origin of the 3-dimensional coordinate system. My gradient of f at xy is the vector fx at xy in I hat direction plus fy, xy in the j hat direction. Fx is given by the partial derivative of f with respect to x, which in this case is 8x minus 2y. Fy is the partial derivative of f with respect to y, and I get negative 2x plus 2y. Fx at the point -1, 5 gives me 3, and fy at the point -1, 5 gives me -8. My gradient of f evaluated at the point -1, -5 is equal to the vector with components 3, -8. This gives me a vector in vector component form of 3i hat minus 8j hat. I want to work another example. If I have a function f of xy that's given by x over the quantity x minus y, I want to compute the directional derivative at the point P given by the coordinates 4, 1 in the direction of the vector given by the components -1, 2. My directional derivative du of my function f evaluated at the points a, b is given by the gradient of f evaluated at a, b dotted with the unit vector u. Fx evaluated at 4, 1 is equal to the quantity x minus y minus x times 1, all divided by the quantity x minus y squared. Plugging in -1 for x and 2 for y gives me fx at 4, 1 is equal to -1/9. Fy at 4, 1 is given by the quantity x minus y times 0 minus x times -1 divided by the quantity x minus y squared. Plugging in -1 for x and 2 for y gives me a value for fy evaluated at the point 4, 1, which is equal to 4/9. My gradient of f evaluated at 4, 1 is equal to the vector with components -1/9 and 4/9. A given vector is not a unit vector. So I'm going to make it a unit vector. I'm going to take the vector given by the components -1, 2, and divide by the magnitude, which is the square root of 5. This gives me a vector with the components -1 over square root of 5 and 2 over square root of 5, so that my directional derivative of f evaluated at 4, 1 becomes the dot product of the vector with components -1/9, 4/9, dotted with the vector with components -1 over square root of 5 and 2 over square root of 5. This gives me a directional derivative that is equal to 1 over 9 times the square root of 5 plus 8 over 9 times the square root of 5, which is equal to 1 over the square root of 5. Now you get to try it. Pause the video and compute the following. When you're ready, restart the video to check your understanding. Given the function f of xy is equal to the natural log of the quantity 1 plus x squared plus 2y squared, compute the gradient at the point P with coordinates -1, 2. And given the function f of xy is equal to the sine of pi times the quantity 2x minus y, compute the directional derivative at the point P given by coordinates -1, -1 in the direction of the vector with components 5 over 13 and -12 over 13. In A, I'm given the function f of x is equal to the natural log of the quantity 1 plus x squared plus 2y squared, and I want to compute the gradient at the point P with the coordinates -1, 2. When I graph this, it looks like a sheet that has been held horizontally with a rock dropped in the middle of it to pull the bottom down. My gradient of f of xy is given by a vector with the components fx at xy, fy at xy. My partial derivative of f with respect to x, fx of -1, 2, is given by plugging -1 and 2 in for x and y respectively to the derivative 2x over the quantity 1 plus x squared plus 2y squared. I do that and my fx becomes -1/5. f sub y at -1, 2 is given by 4y over the quantity 1 plus x squared plus 2y squared, and that gives me 8/10, so that the gradient vector of f evaluated at -1, 2 is the vector with components -1/5 and 4/5. Now I'm given the function f of xy is equal to sine of pi times the quantity 2x minus y, and I want to compute the directional derivative at the point P with the coordinates -1, -1 in the direction of a vector with the components 5/13 and -12/13. The graph of this surface is an oscillating surface that resembles a folded fan. My directional derivative of f at AB is given by the gradient of f at AB dotted with the vector u, which is a unit vector. fx at the point -1, -1 is given by 2 pi times the cosine of pi times the quantity 2x minus y, which becomes -2 pi when I plug in -1 for x and -1 for y. fy at the point -1, -1 becomes -pi times the cosine of pi times the quantity 2x minus y, which becomes pi. My gradient at the point -1, -1 is given by a vector with the components -2 pi, pi. My vector is actually a unit vector, so that my vector has the components 5 over 13 and -12 over 13. This means that my directional derivative of f at -1, -1 becomes -10 pi over 13 minus 12 pi over 13, which reduces to -22 pi over 13. This is how we can work with directional derivatives using the gradient of a function. Be sure and let me know if you have any questions.